In the last lecture, we saw that in the absence of any measure, the sizes of page tables can be huge. Therefore, we studied different techniques by which the sizes of page tables can be controlled. This lecture will start with the discussion on how address translation using page tables can be made faster. What is the motivation? As we discussed, page tables are usually kept in main memory. Therefore, for each data reference, we will typically require 2 memory accesses if we do not take any measure. One access of which will be to access the page table entry itself, and then when we access the page table entry, we get the main memory address, or we get the main memory page number, and we generate the physical address subsequent to that, and then the second memory reference will be to access the actual data that we require from main memory. Now, main memory references are typically very costly with respect to if we had found the data in cache, let us say. Main memory accesses, we said, would be of the order of 50 to 70 nanoseconds, as against cache, which could be around 5 to 10, 1 to 10 nanoseconds, okay, around 5 to 10 nanoseconds. And therefore, it is necessary that we take action to reduce this page table access in main memory. Now, there are 2 typical strategies which are employed here. The first one is to implement the page table in hardware, and the other one is to use a translation look-aside buffer. When we implement the page table in hardware, how do we do it? We implement the page table using a dedicated set of registers, and obviously it is applicable for systems where the page table sizes will typically be small, for example, in embedded systems. Now, during a context switch, when a new process has to be brought into the CPU dispatcher will reload these page table registers along with other registers and the program counter in order to restore the saved state of a process and activate it. So, basically during a context switch, what happens? The saved state of a process is brought into cache. And what is the typical, what do we mean by the saved state of a process? The contents of its page table, the contents of its other registers, and also the program counter. So, therefore, after a context switch, when the process is brought into memory, because we have the saved program counter known, so the process can start from the place where it was previously evicted from CPU. Now, when the page table is in hardware, I have to reload all the registers in page table during a context switch, because that is part of the saved state. If the page table is in memory, it is sufficient to load the page table base register corresponding to this process, because the page table is in memory. I only need where in memory the page table starts. So, therefore, the page table base register only needs to be brought in during a context switch. However, when I am implementing this page table in hardware, I need to bring in the entire set of registers, which is the page table, into the hardware after during the context switch. An example of such hardware implemented page tables is the DEC PDP-11 architecture. The DEC PDP-11 architecture is a 16-bit small computer. So, it has 16-bit logical address space with 8 KB page size. So, therefore, if it is a page 8 KB page size, so therefore, the offset part of the virtual address is 2 to the power 13 bits. So, 2 to the power 10 into 3, 8 KB. So, 2 to the power 13 bits is the size of the page offset part in the virtual address. So, the number of pages is just it consumes only 3 bits. So, 16 minus 13, 3 bits. So, therefore, the page table the system contains only 8 pages, and therefore, the page table consists of 8 entries in fast registers. However, obviously, such hardware implementation of page tables are impractical for computers with very large address spaces. For example, if we have a 32-bit computer and let us say in that computer we use 4 KB pages for example, then I will use 12 bits for the page offset part, and therefore, I will have 20 bits for the page numbers, and therefore, we have 2 to the power 10 into 2 to the power 10, 2 to the power 20 entries in the page table, which is 1,000,000, 2 to the power 20, 1,000,000 page table entries, and obviously, such very huge sizes of page tables cannot be implemented through registers in hardware. Before proceeding, we take an example. A machine has a CPU with a 32-bit address space and uses 8K pages. The page table is entirely in hardware with one 32-bit word per entry. When a process starts, the page table is copied to the hardware from memory at a rate of 1 word every 100 nanoseconds. So, therefore, the page table is in hardware. So, we are trying to look at what is the problem for big computers in a 32-bit computer if the entire page table is in memory. We will look at one of the computers in addition to space. So, the machine has 32-bit address space and it uses 8K pages. The page table is entirely in hardware with one 32-bit entry per 32-bit word per entry. When a process starts, the page table is copied to the hardware from memory at a rate of 1 word every 100 nanoseconds. So, to copy 1 word from memory, it takes 100 nanoseconds. If each process runs for 100 milliseconds and this includes the time to load the page table, what fraction of the CPU time is devoted to loading the page tables? So, the page size is 8K or 2 to the power 13. So, 13 bits we consume for the page tables. So, therefore, the total number of page table entries become 2 to the power 32 minus 2 to the power 13, which is 2 to the power 19, which is 2 to the power 10 into 2 to the power 9 or 524288. So, these many page table entries are there in the page table. All these have to be copied from memory into hardware during a context switch. So, the total time to load the page table will be what? 524288, and each of them consumes 100 nanoseconds. If we convert it to milliseconds, divided by 10 to the power 6, we get 52.4 milliseconds. So, therefore, 52.4% of the total CPU time in this case is spent loading page tables. So, I have a time slot size in which I will execute a process, and I execute a process for 100 milliseconds. For each process I give 100 milliseconds, and out of that 52.4 milliseconds is only consumed for loading the page table from memory into hardware. So, basically I am not being able to do any good work other than loading the page table from memory into hardware, which is very costly. So, therefore, when the page table is in hardware, it is only possible in cases where the address space virtual address space sizes are small and we have a small number of page table entries. So, then what is the other way around when we have large address spaces? So, how to control the time consumed for accessing page tables and doing address translation for large computers with large virtual address spaces, for example, say 32-bit computers? How will we do that? We typically do that using in-memory page tables. So, we do not keep the page tables in hardware, we keep the page tables in memory itself. However, we use the property of the locality of reference of page tables. So, therefore, here is the first point: page table access exhibits good locality of reference. So, therefore, once a page table entry is accessed, it is supposed to be accessed soon again. So, the same page, because our memory references, our memory accesses tend to be clustered in both time as well as space. So, the data that I am consuming, nearby data I can I would consume in the recent future, nearby data I will access in the recent future, and the same data I may access again in the recent future. So, I have both temporal locality as well as spatial locality for page memory accesses, and therefore, the same happens for page table accesses, page table entries. The same page table entries is likely to be accessed soon again. So, therefore, we can use a fast cache for page table entries, and this cache is called the translation look-aside buffer within the CPU. So, we look up the virtual page number in the TLB. So, what do we have? We get the virtual page number is generated by the process, that is the CPU, and I look up that I divide that virtual page number into the page offset part and the page number part. So, the page number part is now floated to the TLB. So, the TLB, this tag part of the TLB contains virtual page numbers. So, we look up the virtual page number in the TLB. If I get a match, with the tag, I get the corresponding physical page number from the data part of this TLB. So, the tag part of the TLB contains the virtual page number, and the data part of this TLB contains the corresponding physical page number. So, when I get the physical page number, I can access the physical memory by adding up with the page offset, which is directly obtained from the virtual address itself. Now, during a hit, what happens? We get the physical page number, and we get and as I said, I can get the data from physical memory. I set the reference bit. So, this one R is the reference bit. I set the reference bit to indicate that in the current time epoch, I have referenced this page to indicate that I set the reference bit. If this I am writing onto main memory, if I am writing onto main memory, I also set the dirty bit on. So, therefore, to indicate that this page has been modified. However, when I get a miss, if my virtual page number does not match with any of the tags present in the translation look-aside buffer, then I have a miss in the page table. Okay. If I have a miss in the page table, I need to get the translation from memory, from the page table. Now, in this case, there can be two distinct cases, that I have a miss in the TLB, but the data is in memory. Therefore, the data is also in the page table, and I just get the translation from the corresponding page table entry in memory, and I bring it back into the TLB, and then reference the TLB again and get the data from physical memory. Otherwise, I can induce a page fault. If the data that I am looking for, the corresponding to the virtual page number, there is this physical page number translation, this virtual page number to physical page number translation is not there in the page table in the memory itself, which means that the page is not there in the memory, I incur a page fault, and therefore, then I need to find out a free page frame in the memory, bring the page from the disk into main memory, and then populate the page table accordingly, and subsequently I need to bring that page table into the translation look-aside buffer, and then subsequently when I access, I get a hit in the TLB, and I get the page number from the TLB itself and use and access the physical memory. So, if there is a page fault, that means that the page is not there in the memory, the CPU raises an exception. That means it traps the OS, it traps to the OS, it generates a trap instruction, and the OS is invoked. I go to the supervisor mode, the OS is invoked to service the fault in the way, as we said, we will see it in more depth in the subsequent slides. However, and if there is no page fault, That means I load the translation from where? From the in-memory page table. From the in-memory page table, I bring the page table entry from the in-memory page table into the TLB and reference the TLB again. I reference the TLB again. Now, I get a hit in the TLB and access physical memory. So, a few more details with the translation look-aside buffer. Typical values for a TLB are as follows. Typical values for a TLB, the size of a TLB are of the order of, let us say, 16 to 512 page table entries. So, page table entries, and each such page table entry could be 4 to 8 bytes. So, therefore, TLBs are typically small in size. The block size for a TLB is 1 to 2 page table entries, and if a page table entry is, let us say, 4 bytes, so 2 page table entries therefore mean just 8 bytes. The hit time of a TLB is very fast, typically of the order of 0.5 to 1 cycle. A miss penalty would result in what? Would result in going to the lower level of memory, and therefore, it will be around 10 to 100 cycles. Why this big difference? Firstly, because different architectures can support different access times, and a miss penalty for corresponding to TLB miss, I may get the data either in the data cache for the corresponding TLB entry, or I may not have the data corresponding to the TLB entry in the data cache. In that case, the TLB entry must be brought from the memory itself. So, therefore, there can be two possible cases when I have a miss and I want to get the page table entry into the TLB. And typical miss rates for a TLB are of the order of 0.01 to 0.1%. So, therefore, the locality of reference for corresponding to TLB entry is typically very high, and so smaller TLBs suffice. So, it is around 99.9% to 99.99% is the hit rate. The associativity of a TLB. TLBs are very often implemented in a fully associative fashion, which means that all the entries of the TLB, so which means that because the TLB is small, I have the option, because the TLB is small, what happens is that when it is fully associative, the page table entry can be brought into any entry of the TLB. Okay. When it is fully associative, I do not restrict the page table entry to go into certain specific locations in the TLB. The entire page table, all entries in the page table can hold any all entries in the TLB can hold any page table entry when it is fully associative. The drawback is that when it is fully associative, all the entries of the TLB must be searched in parallel for the tag. So, therefore, the search time and also the replacement time, as we will see later, becomes high, and therefore, the cost of a fully associative TLB is high, and this is affordable for small TLBs. However, when the sizes of TLBs grow, nowadays we have higher sizes of TLBs, smaller associativities are preferred, okay, as we understand why. Replacement strategies, how do we replace TLB entries when I do not find, when there is a miss in the TLB, I need to replace. So, least recently used TLB entry, if I want to replace, this is typically expensive to implement for large TLBs with high associativity. Why? Because when the TLB sizes are large, finding the least recently used, in implementing the least recently used in hardware, finding which is the least recently used at any time, which entry, keeping that account is expensive. How do we keep account at any time which entry is least recently used? So, therefore, I need to maintain some kind of a clock or a queue corresponding to each TLB entry, and that has to be implemented in hardware, so that at any point in time I can keep track of the least recently used TLB entry. And when the associativity becomes higher, this search or keeping this maintaining this becomes higher, because the number of places within, for example, when it is fully associative, any entry in the TLB can be least recently used. So, I may need to search the entire TLB. In a set associative one, I only need to search within the set. So, therefore, when the associativity is high and when the associativity is high, it is expensive to implement for large TLBs. LRU is expensive to implement for large TLBs, especially and when the associativity is high. So, what is the solution? It is a bypass. What is the solution? The bypass is that we use random replacement. I just find out a TLB and replace it randomly. I do not go for the least recently used. For a TLB, we typically implement write back instead of a write through. So, why do we write? We copy the reference and dirty bits back into the TLB entry on replacement. We said that when there is a TLB hit, what happens is that I may set the reference bit, to indicate that this page table entry was referenced. I may also set the dirty bit to indicate that this page table entry was written to, this page was written to. Okay. Now, when I am replacing this TLB entry, I must write back the reference and dirty bits, the values of the reference and dirty bits into the corresponding page table entry in memory. And I do not do this, and I am using a write back, means that I do not do this writing when I am basically changing the reference or dirty bits at a given page table entry access. That becomes very expensive, because I have to write it back to the next level, to the page table entry in memory if I want to write through, and this becomes very costly. And as we said that the page table miss rates are expected to be small, as we saw, it is of the order of 0.01% to 0.1%. So, page table miss rates are small. So, write back is very good in this case, and it saves a lot of time, and the implementation is much more efficient when we use a write back scheme instead of a write through, and that is I write only during replacement, and I do not write on every reference to the page table entry, every reference to the page table. So, now we will take a deeper look into page faults. So, during a page fault, when I do not have the required data in memory, I incur a page fault. So, at that time the page table entry corresponding to the page table entry corresponding to the page that I want to access shows that it is invalid, that is the valid bit is 0. That means the corresponding physical page number is not mapped to the page table entry. In that case, what happens is that firstly I need to decide whether this translation that I want to do is for an invalid reference or for a valid reference. If it is for an invalid reference, that means that this particular virtual address is not present in my virtual address space itself. This can happen for scattered virtual address spaces of a process. If this virtual address is not part of the address space of the process itself, then this is an invalid reference and we immediately abort. Otherwise, we see that the valid bit is 0 and therefore, the page is just not in memory. So, therefore, it has to be brought from the disk or the secondary memory. So, then what happens? I have to find a physical page frame. I need to find a physical page frame. So, if you see the sequences that are happening here, I try to reference in number 1, I try to reference and I see that the corresponding mapping is not there. It is not there. Therefore, I will have to trap the OS. I will have to trap the operating system to indicate that this is a page fault. Now, the operating system will first find out what kind of trap has it received. So it will then find that this is a page fault type of a trap, and therefore then what the OS will do, it will find a physical page frame in the physical memory. It will find a physical page frame in the physical memory, and then maybe through replacement of an existing page in physical memory, which will not bother right now, we'll see a bit later. Then it will swap page into this frame via scheduled disk operation. So now when I have found a free page frame in physical memory, I will need to bring the page that I require from the backing store or the secondary memory into the physical memory. And I said that how do we get that? In a class, earlier class, we said that in addition to the mapping of a virtual memory corresponding to virtual memory and physical memory, physical page number, the page table additionally logically maybe in a different physical table, it also contains where in the backing store I have this page. That means corresponding to a virtual page number, the page table, in addition to keeping the physical page number, it also keeps the address of where in the secondary memory this page is resident. So when I get a trap, the OS finds out firstly the physical frame where which is free and where I can get the page into the physical memory where I can bring it, and then it finds out where in the secondary memory the page is corresponding to this virtual page number. Then it gets the page from the secondary memory through a scheduled disk operation. So this scheduled disk operation means that for the disk I have a queue of requests. I have a queue of requests who want to access pages from the disk, and I have to go through this queue and get it from the secondary memory, and I have to incur seek time and latency time of the disk, and then through this disk operation I will swap in this page into the physical memory. After I have brought in this page, I know the page number. So therefore I have to reset the tables. I have to reset the tables to indicate that the page is now in memory. So I have to update the page table entry corresponding to this page, corresponding to this virtual page. I will update the page table entry and write what is the current physical page number corresponding to this virtual page number. I will also set the valid bit to indicate that this virtual page is currently now in physical memory. Okay, I will set the valid bit. Then I will restart the instruction that caused the page fault. So I will then restart the instruction. So in a particular memory access, I had a page fault, then I service the page fault, then I will restart the memory, and then in the subsequent memory reference I will get the data that I sought for in the physical memory. Now we will take an example of a practical architecture, which the TLB of a practical architecture. Okay. So we will take a look at the Intrinsity FastMATH architecture, and in this architecture we have 4 KB pages and 32-bit virtual address space. So if we see here, in this virtual page number, we see that it has a 20-bit virtual page number and 12-bit page offset, which means that see this page size is 4 KB, 12 bits. Why? Because right, for 2 to the power 2 into 10 KB. So basically I have using 12 bits I have a page offset of 12 bits, and so the page size is 4 KB. And because I have a 32-bit address space, the virtual page number is 20 bits. Now here we see that the physical page number here, because this one is also of 20 bits, this one is also of 20 bits. The physical page number and the physical address space is also of the same size as the virtual address space. The physical page physical address is also 32 bits. Okay. So, the TLB is fully associative, as we told what it means. It is fully associative and it has 16 entries in the TLB. So, the TLB is fully associative, having 16 entries, and this TLB is shared for instructions and data. So, it is a translation look aside buffer for both instructions and data. Each TLB entry is 64 bits wide. So, this one is 64 bits wide, and it contains the 20 bit virtual address. So, this part is 20 bits. It contains the 20 bit virtual page number. So, this one is 20 bits. It contains the 20 bit physical page number. So, this one is again 20 bits. It contains the valid bit, dirty bits and other bookkeeping bits. So, the total address the total size of one page table entry is 64 bits. If we note, the cache is split. Cache has a split tag and data part. So, basically what happens when there is a TLB hit? When there is a TLB hit, I get the corresponding, let us say the TLB the virtual page number matched in this entry, and I got the corresponding physical page number, the 20 bit physical page number, and therefore, I generated the physical address here. After generating the physical address, I divide the physical address into 3 parts. I split it. One is the physical address tag part, the cache index part and the block offset part. So, to access what? To access the cache. Okay. Now, here now subsequently after dividing this physical address into splitting it into 3 parts, the tag part, the cache index part and the block offset part, I will access the cache, and this cache is implemented again as a split tag and data. So, what happens here? The tag part, if you see here, the tag part is the physical tag part is matched with the tag part of the cache. The tag part of the cache is here. I match it with the tag part of the physical address. I match it with the tag part of the physical address here. I match it, and then if the valid bit is on, I get a cache hit. Okay. Now, at the same time, because I have now split the data part of the cache, what do I do? Why have I done that? I now am, by splitting it, I now am able to concatenate the cache index part and the block offset part as a 12 bit value, and this 12 bit, using this 12 bits, I directly access the data word that I required. I directly access the word. So, if I did not concatenate this, so what would I have to do? I would have to access a given block, and within that block I have to do, because the block offset is contains 4 bytes, which means that I have 16 words within each block. Now, I had to compare this 16 words. I had to compare, because I had to compare these 16 words and using a 16 cross 1 multiplexer to find out which data word I actually need. Now, what happens? I have the tag part. I have the tag part and the block offset part. So, basically I have got the exact data word. I do not have to do this. I do not have to go into the block and then using a 16 cross 1 mux and the block offset. I do not have, using the block offset as the select line, I do not have to use a 16 cross 1 mux with block offset as the select line to know which exact word within this block should I access. I do not have to do this. I do not have to use a 16 cross 1 mux with the block offset as the select line to know which word within the block should I correctly access. Instead, I have concatenated the cache index part and the block offset part to generate a 12-bit value, and I directly access the data. I directly access this data RAM part of the cache and get the required word, and I know that the required word is correct because I have a cache hit here. Okay. So, the desired word in a block, the cache has a split tag and a data RAM. The desired word in a block can be searched without a 16x1 mux by addressing the data RAM with the cache index concatenated with block offset. Okay. Now, in this architecture, a TLB miss is handled in software. So, how do I handle this? If I have a TLB miss, what do? I take the virtual page number and I save it in a hardware register. Then I trap the OS and say that I have a TLB miss. So, based on this, the OS generates special instructions to go into to find the page table entry using the page table base register and the virtual page number part, and the page table base register combination. It gets into the page table entry and brings the required page table entry. Now, the page in a TLB miss requires only 13 cycles in this system when we assume that the code and the page table entry are in the instruction cache and data cache respectively. So, this TLB miss has an overhead of only 13 cycles when the code and the TLB entry are in the instruction cache and in the data cache. Now, we will continue our discussion and take an example here to understand, to illustrate as to how the memory hierarchy works in unison together, how they cooperate among each other and what happens when they work all together. So, memory hierarchy in operation. The example goes like this. In a memory hierarchy organized with a physically indexed, physically tagged cache and physical memory along with a TLB for fast accesses. So, what I have a physically indexed, physically tagged cache, meaning that the cache is addressed by the physical address, it is not using virtual addresses to address the cache, as opposed to other. We will see a technique in the next class, two techniques in the next class, where part of the full or part of the virtual address is used to address the cache. Now, in this hierarchy this does not happen. So, I generate the physical address and then from the physical address I address the cache. So, it is a physically indexed, physically tagged cache. So, I index the cache using the part of the physical address and I tag the cache using part of the physical address. So, I have a memory organized with a physically indexed, physically tagged cache and physical memory along with. So, I have a cache and I also have a physical memory along with a TLB for fast accesses. So, a memory reference can encounter in this system a memory reference can encounter 3 different types of hits or misses. It can encounter a TLB hit or miss, it can encounter a page table hit or miss and a cache hit or miss. So, consider all the combinations of these 3 events. So, you have 8 possibilities, For example, one combination is that a memory reference resulted in a TLB miss, but a page hit and so I have a TLB miss, but I have a page hit and a cache hit. For each possibility, we need to state whether this event can actually occur, whether it is possible in practice that these that a given that an event of a combination of hit or miss will actually occur, and if so, under what circumstances can it occur. For example, can we have a hit in the TLB, a hit in the page table and a hit in the cache? Yes, we can. But obviously, when I have a hit in the TLB, what happens? When I have a hit in the TLB, so this is possible, but we will never look in the page table, because I have a TLB hit. Because I have a TLB hit, we will never look in the page table. Okay. So, and then when I have got it in the page table, I have a cache hit. So, this is possible. So, the page table hit I got, and then I got the physical page number, and after I got the physical page number, I got the data subsequently in cache. Now, I have a TLB hit and a page table hit and a cache miss. This is also possible, but what happens? This is possible, but obviously, I will not check the page table because I have already got a hit in the cache. So, I will not get into memory and actually look into the page table because I have a hit in the TLB. Now, when I have a miss in the TLB, yes, I can have a miss in the TLB, possible. So, I can have a miss in the TLB, and then I will go into the page table lower level of hierarchy and find out whether the page table entry is there or not. And if I have then basically here it says that I have a page table hit. If I have a page table hit, then basically it is in memory, and if it is in memory, it may or may not reside in cache. In this case, I am saying that it is a hit in the cache. So, it is in the hit in the page table, therefore, the data is in memory, and it is a hit in the cache. So, the data is also in the cache. So, this is possible. The next case, I have a miss in the page, I have a miss in the TLB, I have a hit in the page table, and I have a miss in the cache. Yes, this is also possible. As we said, I have a miss in the page table. So, I get to the next level, get the page table entry. I find that the page table entry, the actual page actually resides in physical memory. However, when I generate the physical address, break into tag, cache index, block offset, etc. for accessing the cache, I see that the data is not present in cache. So, therefore, I have to incur a memory reference, physical memory access, and get the data from physical memory. I will not get it from the cache directly. It is also possible that I will have a miss in the TLB. Subsequently, I will look into the page table, and I see that the data is not in the page table. So, therefore, I will basically the data does not reside in the main memory, and I'll also have a miss in the cache. So, this is also possible. So, I will obviously, because there is a page table miss, I will also have a miss in the cache. It cannot be that my page table it is there, it is not there in the main memory, or data is not there in the main memory, but the data is there in the cache. This cannot happen. Now, let us see the next case. I have a hit in the page table, but I have a miss in I have a hit in the TLB, but I have a miss in the page table. Is this possible? This is not possible, because if I have a hit in the TLB acts as a cache for the page table. So, if I have a hit in the TLB, the data must also be there in the page table. The entry must also be there in the page table. So, it is not possible that I have a hit in the TLB, but I have a miss in the page table. Similarly, this is also impossible. It cannot be that I have a hit in the TLB and a miss in the page table. I have a miss in the I have a miss in the TLB, I have a miss in the page table, and but I have a hit in the cache. Is this possible? This is also impossible. Why? Because I have a miss in the page TLB, fine. So therefore, I have a miss in the page table. This part is fine. However, I have a miss in the page table means that the data, I have a page fault. I have a miss in the page table means I have a page fault. So the page is not resident in main memory. So when a particular page is not resident in main memory, the corresponding block cannot reside in the cache. So this is impossible. So we will end this lecture with a small example. If an instruction takes time m if there is no page fault and time n if there is a page fault, what is the effective instruction time if page faults occur every j instructions? So we see that time m when page hit, I have a page hit, and time n when I have a page fault. Okay. So now I am saying that in a group of j instructions, I have one miss and the all other are hits. So in this system, page faults occur once every j instruction. So for j minus 1 instructions, I have the time required is m, and for one instruction the time required is n. So every j instructions, what happens is that for j minus 1 instructions I take m time, and for one other instruction I take n time. Okay. So therefore the effective instruction time, so what is the average instruction time? Then the average instruction time is given by this. So this is basically m plus what? M plus n minus m by j. So this is the effective instruction time. With this, we come to the end of this lecture.